In this video, we will learn how to solve a system of two linear equations in three variables. When talking about solving linear equations, it's important to note the three different types of solutions and their corresponding outcomes. The first type of solution is the independent solution. In this case, the lines will have different slopes and therefore intersect only once. Since these lines only intersect once, there is only one solution to this type of system. The second type of solution is the dependent solution. The lines defined in this system of equations will coincide, meaning they have the same slope and the same y-intercept. This gives us infinitely many solutions. The third and final type of solution is an inconsistent solution. Here the lines have the same slope but have different y-intercepts, making them parallel lines. This type of system does not have a solution. We can solve systems of two linear equations in two variables, as well as systems of three linear equations in three variables. But what happens if we have a system of two linear equations in three variables? In this case, the two linear equations will always correspond to two planes in three dimensions. As a result of this, our only possibilities are no solution, meaning the planes are parallel, or infinitely many solutions, meaning the planes intersect in a line and the points on that line are the solutions. Let's do an example where we solve a system of two linear equations in three variables. We are given the equations 3x plus 5y minus 4z equals 3 and 2x minus y plus 8z equals 1. To keep track of them, let's label the first equation 1 and the second equation 2. In order to eliminate z, we should look for the least common multiple of 4 and 8, which is 2. Multiplying equation 1 by 2 gives us 6x plus 10y minus 8z equals 6. We now have a negative 8z in equation 1 and a positive 8z in equation 2. By adding the two equations together, we can cancel out the z terms. This gives us 6x plus 10y minus 8z equals 6 plus 2x minus y plus 8z equals 1. The z terms cancel, giving us 8x plus 9y equals 7. Therefore, equation 1 and equation 2 are both true if 8x plus 9y equals 7. Since we know there is a solution, we know the solution has to be a line. From here, we can solve for either variable numerically, so we'll use a parametric representation. For simplicity, let x equal a, where a can be any real number. Now we can solve for y in terms of a. So, we have 8a plus 9y equals 7. Subtract 8a from both sides to get 9y equals 7 minus 8a. Solving for y, we get 1/9 times the quantity 7 minus 8a. Now that we found x and y, we can find z. So far, we have x equals a and y equals 1/9 times the quantity 7 minus 8a. Substitute these expressions into equation 2 to find z. This gives us 2a minus 1/9 times the quantity 7 minus 8a plus 8z equals 1. First, distribute the negative 1/9 to eliminate the parentheses. Then combine the a terms to get 26/9 a minus 7/9 plus 8z equals 1. Add 7/9 to both sides and subtract 26/9 a from both sides to get the z term alone. Finally, divide both sides by 8 to get z equals 1/36 times the quantity 8 minus 13a. Now that we've solved for all three variables, we can write the solution. The solution is the line in three dimensions given by a, 1/9 times the quantity 7 minus 8a, 1/36 times the quantity 8 minus 13a, where a is any real number. As an added note, we can say that any real number a corresponds to a point on the line of intersection.